Bernoulli's equation. You might have heard of this before. A lot of science fair projects, including one that I helped my grandson on a couple years ago, are on Bernoulli's equation, Bernoulli's law, Bernoulli's principle. Got a lot of different names. So we're going to add another adjective to our list of adjectives that we describe flows with. Steady, we've talked about a couple of times. Incompressible means you can't squash it. The density is always the same. And now we're going to add another one, inviscid, meaning that it's not viscous. You can ignore the viscosity of the flow. The viscosity is the resistance to shear in the flow. If you think about honey, if you put honey on the table and you put a book on top of that layer of honey, it's hard to push that book along the layer. And the reason is viscosity, resists the motion. But we're going to ignore that in this particular concept. The pressure P, speed V, elevation Y, and density rho at 2 points are related by the following equation. P1. So here's point 1. Here's point 2. Pressure at point 1. Pressure at point 2. The pressure at point 1 plus 1/2 rho V1 squared. This looks like ½ mv squared. And this is one way that helps me remember this equation. This looks like mgh. This term here, if you replace the rho with an m, looks like a kinetic energy. This term here, if you replace the rho with an m and the y with an h, looks like potential energy. In fact, this is the kinetic energy per unit volume, because if I take this and I divide by a volume, mass per unit volume is the density. So that is a kinetic energy per unit volume, and this is a potential energy per unit volume. And this is a pressure. So pressure plus kinetic energy per unit volume plus potential energy per unit volume equals the same thing evaluated at some other location in the fluid. That's the Bernoulli equation. It's very powerful. It's a statement of, it follows from the work energy theorem, and it is a statement of conservation of energy for fluids. So what does it say? If the height, so here's y1 and here's y2. So they're measured from the same spot, measured as 0 at some common location. If both of those are the same, y1 equals y2, then this y1 equals this y2, and these two terms cancel each other. So in this case, where they're both high, both at the same height, both points are at the same height, you've got just two terms on each side of the equation, the pressure and the 1/2 rho v squared. Well, what that says is that if the velocity is high, if you increase the velocity, then you have to decrease the pressure, because this quantity, the sum of the two, has to be a constant in the fluid. So increasing the velocity means decreased pressure. And that's what we've said here. A high velocity means low pressure. And vice versa. A low velocity means high pressure because you have to add up these two terms and always get the same thing out of those two terms. So for example, this case here, we expect a high velocity here at point 1 where the pressure is P1. That means this high velocity means that the pressure is going to be low there. So here the pressure will be low and this velocity will be high, but over here at point 2, the pressure is high and the velocity is low. We already know that the velocity is low by conservation. The volume flow rate has to be conserved. We already talked about that and did an example. The velocity has to be low. Bernoulli's equation says that the pressure has to be high. And you say, well, just a second here, Dr. Edwards, because that seems counterintuitive to me. To me, the pressure should be high at this nozzle because it's creating that high velocity. And here's a case where your intuition fails utterly. We'll do a demonstration to show that your intuition does fail you. This actually has lower pressure than this. Here's where the high pressure is. One example of that is varicose veins, where a vein gets enlarged, the pressure actually is high there, and it continues to enlarge more. And that's a cause for varicose veins. It doesn't balloon out where it's narrow, it balloons out where it's big. So so also there's a dependence on the elevation. If you get up higher, you'll be at a lower pressure. And that's just the whole gravitational potential energy type of an idea. It's actually seen in the equation that we derived for the static pressure. The higher you go, the lower the pressure is until you reach the surface where it's atmospheric pressure. So that's the same idea that comes in here. In fact, if you just look at this term and this term and this term and this term, if you say that y2 minus y1 is h, then, I'm sorry, y1 minus y2 equals h. Let's see. P2 equals P1 plus rho g y1 minus y2, and replace this by h, then we've recovered the equation that we had before. P2 is P1 plus rho g h. Here h and y serve a similar function, but h is the difference between two heights. Okay, if you still don't believe me, here's a demonstration. This is a Venturi tube. I've got a source of air that'll come in to this side of the tube. It'll pass through this region where the tube is wide, and then here where the tube is quite narrow, and then back to wide again. Since the same amount of air has to pass through this wide cross-section as passes through here, namely the volumetric flow rate has to be the same. The number of cubic centimeters per second passing this spot has to be the same as the volumetric flow rate that passes this spot. And because this spot has a smaller cross-sectional area, the air has to flow faster here. So we've got a high velocity region here, a low velocity region here. But Bernoulli's principle says that the higher the velocity, the lower the pressure. So in this spot here, contrary to what your intuition might say, instead of the pressure being high here, the pressure is actually low. And we can demonstrate that using this colored water. I've filled the bottom of these this U-shaped glass tubing with water that has a little bit of food coloring added to it. What you'll see is when we turn on the air, this column of water in the middle will rise because the pressure here is lower and essentially acts as a suction for for the water. So this one will rise higher than either of the other two. So that's a Venturi tube, a demonstration of the Bernoulli's principle, and very important in a lot of areas of fluid dynamics. All right, conceptual example. When a truck is stationary, the tarp on the truck is flat. So if it's just sitting here, but it bulges upward and the truck moves down the highway. Why is that? Well, as it's moving down the highway, the truck's velocity is this way. It's moving through the fluid, but from the truck's perspective, the air is rushing over the top of the truck, as well as below the truck and along the sides of the truck at a high velocity. So above the tarp, the velocity is high, and the pressure must therefore be low. Below the tarp, in whatever's between the well, you've got air between the tarp and whatever the contents are in the trailer. The air is not moving at all, or at least not as much as it is on top of the tarp. You'll have a low velocity and a high pressure. So you get high pressure below and a low pressure above, because it's high velocity. So high V and a low P on top. And here we have a low V and a high P. So the pressure is higher underneath. That causes the tarp to come up. Another demo showing how Bernoulli's principle works. High velocities, low pressure, it raises the paper up. This is another demonstration of Bernoulli's principle. I'm going to create a stream of air using this hose and send it across this piece of paper that's been taped to the tabletop and is dangling off of the edge of the tabletop. What you'll be looking for is what you'll be thinking about, hopefully, is that the velocity will be high on the top side of this paper. That high velocity means the pressure will be low. And the pressure on the bottom side of the paper is atmospheric pressure. And so it will be greater than that low pressure on top, and the atmospheric pressure will push the piece of paper up and overcome the small amount of weight that this paper has and bring it into a vertical position just below the stream of air. This is how a clarinet reed works. When the stream of air from the player's mouth goes over the reed, it creates a low pressure region which causes the reed to move. And then when the air goes the other direction, the reed moves in the other direction. So that causes the reed to vibrate and causes the instrument then to sound. Yeah, so we've now got the paper up. We've got high velocity and low pressure here. I can disrupt it and the paper will go down. And this is actually a principle upon which a lot of musical instruments work. The lips of the trumpet, there's a Bernoulli effect that is relevant there. The Tacoma Narrows bridge collapse, same thing. The air stream over the top of the bridge will cause a lower pressure and the bridge to rise, and that's what caused that Tacoma Narrows bridge to come down. This is the way airfoils work. What happens in an airfoil is that two air molecules, one that ends up going above the wing and the other one that goes below the wing, the one that ends up going over the wing travels a farther distance. than the one that's below the wing. And if they meet up after they both made their trek across the airfoil, if they meet up at the same time, so they started out together and they end up together, that would be a streamlined flow, a steady flow. Then that would mean, in order for them to meet up after their journey is over, that would mean that the guy on the top had to be traveling faster. If he's traveling faster, that's a high velocity, and the pressure must therefore be lower by Bernoulli's principle. And down here, we have a low velocity and a high pressure. So what that says is there's a higher pressure pushing up on the wing than there is pushing down on the wing. This is a low pressure pushing down and a high pressure pushing up. Which one wins? Well, the one that's pushing up. That's what provides the lift for the wing. That's only usually 30 or 40% of the lift provided for wings. The other way that you can provide lift is by putting these ailerons down or actually just tilting the wing up so that the air hits it and reflects downward. That's called dynamic pressure. But this Bernoulli principle is an important piece of the puzzle. Another demo of Bernoulli's principle using a spool and a paper. This is a simple demonstration, one that you can do at home, a demonstration of Bernoulli's principle. I have one of my wife's spools for thread. I have a pin, and it's stuck through a piece of just construction paper. All there is to it. You can amaze your friends and neighbors with this one. Hollow out the spool, put the pin through the spool, and the part that's not so really amazing is if you suck up through this hole, the paper will, of course, because of the suction, I'm evacuating the hole here, and the paper is sucked up because of that, because the pressure below is atmospheric, and I've created a small vacuum in here. The more interesting one, the one that demonstrates Bernoulli's principle, is when you blow down, vertically down through this hole. So it seems unexpected that you would have thought that the air coming down through that hole would blow the piece of construction paper away from the spool. But it's not what happens. What happens instead, if this is the spool and this is the piece of paper, the airflow goes down through that center hole, hits the piece of paper, and exits to either side. Well, it exits radially in all directions, so it's coming down through here and going out in all directions. Because the velocity is high here, the pressure must be low by Bernoulli's principle. So you have a low pressure up in this region between the paper and the bottom of the spool, but you have high pressure, or normal pressure, atmospheric pressure, down here. So the pressure pushing up on the paper is greater than the pressure in this region, and that difference in pressure, the high minus the low, is what holds the paper in place. And that actually counteracts the effect of the air hitting the surface. The air will hit the surface and will cause an impulse, like a rocket when it's shooting out its fuel. Hitting this surface actually pushes it down. But this pressure effect, which is due to the Bernoulli principle, is the greater of the two effects and holds it in place. Yet another demo. This is a demonstration of Bernoulli's principle. I taught for 24 years in West Virginia, and our home in West Virginia had a heat vent that was on the floor, and so the hot air came up through that vent into the room. And one day the kids had a balloon, and that balloon was balancing in midair above that heat vent. And I thought, well, how in the world does that work? And it's actually quite interesting. So this is the phenomenon. We've got a stream of air that comes up vertically, in the case of West Virginia, through the heat vent. And then you've got a rather light object, in that case a balloon, in this case a foam ball, that's perched and being balanced and levitated by that stream of air. The principle is that the uprushing air holds the ball up. There's some momentum transfer when the air hits the bottom of the ball, and it holds it up. So that part is not so mysterious. The part that is mysterious, and was to me, was what happens if that ball gets off-centered? So let's say it moves to the left, and this shows the uncentered situation with the ball to the left and the stream of air going past it on the right. Well, why does that ball want to move back into that rushing air? You'd think that it wouldn't want to move back into the air, and it would just fall off to the side. But what happens is that Bernoulli's principle comes into play. Over here, there's a lot of air on the right side that's rushing past the ball. And Bernoulli's principle says that if you have a high velocity, a high airspeed, then you have a low pressure. So this air on this side of the right side of the ball exerts a smaller amount of pressure on this ball than the atmospheric pressure does on the other side. So this arrow represents the atmospheric pressure pushing the ball to the right, and this represents the less than atmospheric pressure that tries to push the ball back to the left. The atmospheric pressure from the left wins and pushes the ball back into the centered configuration, where now you've got equal pressures on each side and the ball is happy. So you can take this up to any scale that you want to, including this rather large scale demonstration. And that is Bernoulli's principle. Plumbing systems. We're building a house now in North Logan, and the builder, Sierra Holmes, puts near each sink puts a pipe, a vent to the outside. What's the purpose for that? Well, our current house in Logan, sometimes there's a sewer smell that comes up in the kitchen sink. And why is that? If there's another appliance like a dishwasher nearby, what happens is that if the washing machine or the dishwasher or whatever has a high velocity flow through this point, high velocity and low pressure. Well, that low pressure region can well, actually, let's look at it over here. Without a vent, you get a high velocity and a low pressure. I don't think you can read that, but that says high velocity, low pressure. What happens, you get a high velocity passing through here, you get this trap, and what that can do is it can empty out the trap. It can suck that fluid from the trap here, allowing the sewer gases to come up into the sink, which is disgusting. So what you do instead is you vent it to the outside so that when you've got a high velocity here, the pressure is forced to be the atmospheric pressure outside, and it doesn't empty this trap. Wise practices based on physics, wise construction practices. Physics of baseball. If the ball isn't spinning, then it just moves through the air, and well, with a knuckleball, if it's a knuckleball, then you get some cool patterns across the stitching, which can cause the ball to move erratically. But if you do a curved ball, and the ball is spinning in this direction, what it does is the ball kind of carries the air and encourages the flow across the top side of the ball, whereas the ball moving this way is opposite to the direction of the flow of air crosses it, and so it slows the air here. So we get a low velocity and a high pressure. And up here we get a high velocity and a low pressure. So on this side of the ball we have a low pressure, on this side of the ball we have a high pressure, so there's a net deflection force that causes the ball to curve. That's how curved balls and how they work. So here's a demo of this effect. So on that last one, it's interesting, the batter thought the ball was coming toward him and he ducked, and it went clear to the other side of the home plate. Fascinating. All right, another example. A tank is open to the atmosphere at the top. Find an expression for the speed of the liquid leaving the pipe at the bottom. So in this particular case, we're looking at atmospheric pressure up here on the top. Atmospheric pressure on the top, but we're also allowing this to exit the liquid at the bottom. So there's going to be atmospheric pressure at the bottom. Now you say, well, hang on, what does that happen? Doesn't the pressure increase with depth? And it does. So there'll be increasing pressure as we get deeper and deeper, and then as we go between here and here, the pressure is going to be atmospheric again, because it's open to the atmosphere, and anything that's open to the atmosphere is at atmospheric pressure. So how fast is this going to be going? So here's how to do this problem. Pressure 1 and pressure 2 at the two different points. So here's point 2 at the top, here's point 1 at the bottom. Both of those pressures are going to equal atmospheric pressure. So P1 equals P2. So we can cancel them out. They're both equal to the same thing. And the difference between the heights, y2 minus y1, we're just going to call h. So I'm going to subtract this term from both sides of the equation, and we'll get rho g times y2 minus y1, but that's h. So that's this term right here. And then we're going to ignore, I mean, certainly the velocity at 1 here is huge. But the velocity up here is essentially 0. It's moving down a little bit, but compared to this velocity, it's negligible. So we're going to ignore the velocity v2 and set it to 0. And that leaves us with 1/2 rho v1 squared equals rho gh. And that allows us to calculate the speed of the water where it exits down here.